Hello everyone, this is S.K. Mehta, presently the President of the Indian Nuclear Society, called INS, established in 1998. I wish to welcome you all to this INS series lectures. This series, about 13 lectures, is aimed to acquaint you with the various aspects of nuclear energy, its utilization in various areas benefiting humanity, the limitations and the regulatory aspects in safety and protection. One of the main objectives of the INS is to promote the advancement of nuclear science and engineering and technology related to the atomic nucleus and the allied sciences and arts. With this objective, INS has been disseminating information through journals, books, reports, newsletters, seminars, and conferences. These have mainly been to keep the INS members and other scientific communities and organizations well informed about the development in the various areas of science and technology within India and world over. All it is realized that there is a need to keep the various professionals, undergraduate students, and general public knowledgeable in their respective fields of nuclear science and engineering. For the benefit of the public, some of the important and the common application of nuclear being for power, industrial use, medical diagnosis and treatment, agriculture, food preservation, and various other areas. This lecture series is made in simple language and illustration with the aim to inform the general viewer about the science, engineering, and technology, social benefits of the nuclear, application of nuclear carrier benefits in nuclear and regulatory and safety of the nuclear energy. The presentations are prepared and narrated by experts on each topic in a way that the viewers with no background knowledge about the nuclear science and engineering can understand. Our effort will be to constantly provide information about newer benefits to the society emerging out of the painstaking research and nuclear science and engineers. Viewers are encouraged to comment, suggest, and put forward questions to the experts. The channel of the constructive communication will always be open in INS, which is website ins-india.org.
Hello everyone, I am Argala Srivastava. I belong to Bhabha Atomic Research Center. I work on the design and analysis of nuclear reactors. Today I will be speaking on the history of nuclear reactor development. So let's travel through this fascinating journey of what nuclear reactors are and how and when they were originally made. Nuclear reactors are primarily used for the generation of electricity. Electricity is one of the greatest gifts that science has given to the humankind. Almost everything in our world depends on electricity. So let us find out what are the ways electricity is produced. We have hydroelectric power generated from water, which falls from a great height in the hydroelectric power station. But the major issue with the hydroelectric power is that it requires a large flooding area, which causes deforestation, loss of wildlife habitat, and change of the course of river. We know of wind turbines, which uses the energy of winds to rotate the turbines. You would have seen windmills along the hillsides. Windmills cause noise pollution and have an environmental impact. Then we have solar power, which harnesses the energy of the sun but is dependent on the weather conditions. It needs very large land for solar panel installation and is not power generation intensive. Now we have thermal power. Thermal power is at present the major contributor to electricity generation. In a thermal power plant, water is heated in a furnace to a heat source, basically a coal, and it produces steam. The steam which is produced in the furnace is used to rotate the turbine, which then drives the generator and produces the electricity. But the major issue with the thermal power plant is that the fossil fuels like coal and petroleum, they are non-renewable. They will be exhausted in the near future and are a major source of global warming. Now, what about nuclear power? Nuclear power uses nuclear reactions to produce electricity. A nuclear power plant is very similar to a thermal power plant. The Only difference is that instead of using coal to heat the water, the heat from a nuclear reaction is used to produce the steam. Therefore, there is no carbon emission that affects the environment. It is thus a clean source of energy. So, it is worth knowing about how nuclear reactors can power the world without harming the environment. Just as coal is mined from the ground, something called uranium ore is also found in the earth. About 85% of the uranium ore is produced in Kazakhstan, Canada, Australia, Namibia, Niger, and Russia. India too has uranium deposits at Jadugura and Tumbalpalli mines. This is one of the pictures of the uranium mines in India. 1,000 kgs of uranium ore produces 65 grams of usable uranium. This uranium ore is then converted into a chemical form which is commonly known as yellow cake. This yellow cake is further processed in the form of black powder, which is then made into fuel pellets. These fuel pellets are of the same size of a sugar cube, but it contains as much energy as thousands kgs of coal. Now, this uranium fuel contains millions of uranium atoms. We all know what is an atom. Everything around us is made of these tiny fundamental bits called atoms. Atoms are so very small that they cannot be seen with a naked eye or even with the most powerful of microscopes. This is an enlarged view of atoms in the uranium fuel. At the center of atom, you have a nucleus, and surrounding it is a cloud of electrons, and electrons are negatively charged. Now, the dense portion called the nucleus is composed of two types of particles, neutrons and protons. Protons have a positive charge while neutrons do not carry any charge. Now, number of protons and neutrons define the type of atom or the nucleus. For example, uranium atom or a nucleus is represented by an alphabet U. The number 235 represents the total number of neutrons and protons in the uranium nucleus, while the number 92 represents the total number of protons in the uranium nucleus. We know that if we bring two particles of same charges together, they repel each other. So, if protons and protons are brought closer to each other, they will start repelling and they move far apart. You may wonder that how protons within the nucleus, how they are bounded to each other, why they are not repelling, or why the nucleus is held together. The neutrons and the protons in the nucleus are held together by strong attractive force acting between them. So even though protons repel each other in the nucleus, there is a strong attractive force between neutrons and protons. And this strong attractive force overpowers this repulsive force acting between the protons. This force is called the nuclear force. This nuclear force is stored in the nucleus in the form of binding energy. So let us understand what is this binding energy. Neutrons and protons, which constitutes the nucleus, they have their respective masses. Mass in the common term means weight. So the weight of the nucleus which is formed should be ideally equal to the total weight of the neutrons and protons constituting it. But it was observed that when a nucleus is formed from the neutrons and protons, the sum of the masses of the neutrons and protons is more than the mass of the nucleus formed. So there is a loss in mass. Where this lost mass has gone? This loss in mass was explained by the theory given by a famous scientist, Albert Einstein. During 20th century, Albert Einstein came up with the revolutionary theory that mass and energy are interconvertible. That means the mass can be converted into energy and energy can be converted into a mass. He gave a famous equation E is equal to mc square. You might have seen this equation at many places, which means that energy is related to the mass of the particle by a constant c square, where c is the speed of light. He explained through this equation that this loss in mass of the nucleus is released in the form of binding energy. So, when a nucleus is formed from its constituents, neutrons and protons, some mass is released in the form of binding energy. In the year 1938, physicists Otto Hann and Strassmann made a startling discovery that the uranium nucleus when bombarded with neutrons, splits into two lighter nuclei and emit few neutrons and radiation. Along with them, a huge amount of energy is released in the form of heat. So you may wonder from where this heat has come from. This heat has come from the binding energy stored in the nucleus. The uranium nucleus and the lighter nuclei which are formed, they have their respective binding energy. They have their own binding energy. As I have stated earlier, that each nucleus has its own binding energy. So the binding energy of the lighter nuclei which are formed is more than the binding energy of the uranium nucleus. So this difference in the binding energy is released in the form of heat. This phenomena of splitting up of a uranium nucleus into two lighter nuclei with the emission of neutrons, radiation and with lot of energy is known as nuclear fission. It is interesting to know that the energy released by burning 1 gram of carbon is 8,000 calories, while the energy released by the fission of 1 gram of uranium is million times more. The discovery of fission by Hann and Strassmann completely revolutionized the field of nuclear science. It also became clear with this discovery that besides the immediate release of energy, some neutrons are also emitted out in a nuclear fission. These neutrons play a very crucial role in the production of nuclear power. So let us understand why these neutrons are so important. Let us assume that we have got neutron from some source. Now this neutrons enters into the uranium pellet and this pellet contains millions of uranium nucleus. Now the neutron causes the fission in a uranium nucleus and splits it into two lighter nuclei and produces heat and few neutrons. These neutrons further enter into other uranium nuclei present in the uranium pellet. They again cause the splitting of the uranium nucleus and enormous heat is produced. And this chain of production of heat and neutron continues to go on. It is like a cascading effect, like a forest fire. It starts at one place but spreads in all the directions and continues to grow unless controlled. So this cascading phenomena is called the fission chain reaction, and enormous heat production by the chain reaction is converted into nuclear power. Now, observing the chain reactions of fission, where a great amount of heat is being produced, scientists realized that this heat could be used beneficially for the generation of electricity. Therefore, the next logical step was to collect enough uranium together to carry out a continuous chain reaction. And this led to the top secret mission called the Manhattan Project for harnessing the enormous power of the uranium atom. In December 1942, Enrico Fermi, with a small group of scientists, gathered beneath the football stadium of Chicago University for an experiment to create a fission chain reaction. Scientists built the pile structure by stacking layers of material called graphite on top of a wooden frame. They call this structure as Chicago pile. The graphite bars were fitted very close to each other. Some graphite bars were drilled with holes to fit lumps of uranium to start the fission chain reaction, while some were filled with special rods called the control rods or the safety rods to control the fission chain reaction. On achieving the first sustained fission chain reaction, a secret message was delivered to the higher authorities that the Italian navigator has just landed in the New World. It is very interesting to know what is the significance of Italian navigator and the New World. We all know about Christopher Columbus. He was an explorer. He was an Italian navigator who discovered America in the year 1492, which was then called the New World. The Italian navigator has just landed in the New World draws a parallel to Enrico Fermi, who was also an Italian. He migrated from Italy to America and worked on the Manhattan Project during World War II. Enrico Fermi, with a small group of scientists, created a history. They achieved the first fission chain reaction and controlled it. Chicago pile became the world's first nuclear reactor. Once the enormous potential of nuclear fission was realized, rapid efforts were made to use nuclear energy for producing electricity and for the propulsion of ships and submarines. In 1951, the first production of usable nuclear electricity in Idaho National Laboratory, USA, was demonstrated in the experimental breeder reactor EBR-1. The electricity that lit up 200-watt bulbs had been strung across the test area. By 1954, Argonne National Laboratory, USA, launched the first nuclear-powered submarine, USS Nautilus. It sailed 50,000 miles with uranium fuel carried on board and not refueling. It traveled underneath the polar ice cap. USS Nautilus demonstrated that the nuclear power was both safe and reliable. In December 1953, US President Dwight Eisenhower addressed the UN General Assembly in New York in his famous Atoms for Peace speech to promote the peaceful uses of nuclear energy for the benefits of all mankind. He proposed the formation of International Atomic Energy Agency (IAEA). Under the watchful eye of the IAEA, several nuclear reactors were built in the ensuing decades for producing electricity using the experience and technology developed during submarine development program. Now we have understood the basic process of fission and that the energy produced as a result of fission is used for generating electricity. Now I am going to give you an idea how this electricity is produced in a nuclear power plant and what does a nuclear power plant looks like. Now, the nuclear power plant comprises of a nuclear containment and a cooling tower. Reactor containment or the nuclear containment is the structure that contains the nuclear reactor and separates the nuclear reactor from the environment. They are typically dome-shaped, as you can see in the figure, and they are made up of steel and concrete. Cooling towers, which these are the two cooling towers, they are used to remove heat generated in the nuclear reactor. Cooling towers just give out water vapor to the atmosphere, nothing else, and they do not contribute to the climate change. Now, coming to this dome like structure, nuclear containment or the reactor containment. This is the actual picture of the reactor containment, and this is a schematic view of the reactor containment. Now, reactor containment consists of a reactor pressure vessel. Reactor pressure vessel is a vessel inside which the nuclear reaction takes place. The fission reaction takes place and the heat is generated through fission. Then we have a main coolant line. Basically, it is a pipe which carries a liquid which is called coolant, and this coolant is circulated through the reactor pressure vessel. It carries away the heat which is produced in the reactor pressure vessel. Then we have the reactor coolant pump. It provides a forced primary flow to remove and transfer the amount of heat which is generated in the reactor pressure vessel. Basically, it's a simple pump which gives a velocity to the coolant to flow across the reactor pressure vessel. Then we have pressuriser. This is a pressuriser. The liquid in the main coolant pump is kept under some pressure to prevent it from boiling. Because if a liquid boils, it will not take away the heat from the pressure vessel. So it is prevented from boiling by keeping it under some pressure. A pressurizer is basically used to maintain the required pressure in the coolant pipe. Then we have something called steam generator. The steam generator, as you can see in the figure, is used to convert the liquid into steam from the heat produced in the nuclear reactor. Let's find out what a reactor pressure vessel consists of. We have seen this reactor pressure vessel in the previous slide. Let us see what does it consist of. This is the actual picture of a reactor pressure vessel. It looks like this. And we have a schematic diagram of that. So a reactor pressure vessel consists of, first of all, fuel. I have spoken about fuel pellets in my earlier slides. These fuel rods, they are made up of fuel pellets and they are fabricated in a form of rod. They are inserted into the reactor pressure vessel and it is within this rod that the nuclear fission takes place and the heat is produced. The material which is used to fabricate these fuel rods are uranium, which are mined from the uranium mines. And then there is one more material which is used to produce nuclear heat from nuclear fission, which is artificially made and it is called plutonium. This is man-made, it is not found in the mines. The next is the coolant. I have already spoken about it. The main coolant line consists of this liquid which takes away the heat which is produced in the reactor pressure vessel. The material which is used as a coolant in the nuclear reactor is common water, and there's heavy water, and other material is sodium. They take away the heat which is produced in the reactor pressure vessel. Then you have moderator. Moderator is also a kind of a liquid which is filled in the reactor pressure vessel. Now the neutrons which are produced in the nuclear fission, I have already spoken about them, they have a very high velocity of few kilometers per second. Now in order to make it more efficient, that so that they can produce more and more heat from the fission reaction, they need to be slowed down, they need to be moderated. So moderator is a material which is used to reduce the speed of the neutrons from few kilometers per second to few centimeters per second. So these materials are called moderators, and they are filled in the pressure vessel. So when the neutrons are produced from the fuel rods, they see these moderator, they lose their energy and they become slow, or we call them thermal. They become thermal, and when they again enter into the fuel rods, they have a slower velocity and they produce the heat, or they cause the fission more efficiently. So the moderators which are used in the nuclear pressure vessel are water, heavy water, and graphite. Then we have control rods. Now these control rods are basically the rods which are inserted from top in the reactor pressure vessel, and the main function of these rods is to control the chain reaction or to stop the chain reaction. So materials which are used as control rods in reactor pressure vessels are boron, cadmium, and stainless steel. So let's look at the full picture of the nuclear reactor again. To start with, we have fuel rods inserted inside the pressure vessel. The reactor pressure vessel is then filled with moderator. The fission chain reaction starts, and with the help of control rods, these control rods, we are able to maintain the fission chain reaction within the pressure vessel. At this point, when the fission chain reaction has started inside the pressure vessel and is maintained, the reactor is said to be critical. This is a very important term in the nuclear reactor physics community, that when we have achieved the controlled fission chain reaction, we call that the reactor is critical. While the word critical may sound alarming to you, it merely means that the important point of control chain reaction has been achieved, and it is a matter of achievement for us. Now, once the heat is produced in the reactor pressure vessel, it is carried away by the coolant. It is then converted into steam by the steam generator, and then this steam is used to drive the turbines. Now, the power produced by the turbines is expressed in megawatt thermal. These turbines are then coupled to the generators, which then produces the electricity. The electricity which is produced, or we can say the thermal energy which is converted into the electrical energy, is expressed in the units of megawatt electrical. It should be understood here that only 30% of the thermal energy is being converted into electrical energy, and rest is lost to the environment. This electrical energy is then supplied to the grids. Depending on the usage, nuclear reactors are classified into two categories: research reactors and power reactors. Research reactors are used for the scientific research and experiment purpose, while power reactors are used to produce electricity. This is the actual picture of a swimming pool type of reactor. In a swimming pool type of reactor, the fuel rods and the control rods, they are immersed in a large pool of water. You might have seen in the science fiction movies that the nuclear reactors always glow. While the movies use special effect, the glow is based on a scientific fact. The water surrounding the fuel rods in a nuclear reactor actually glows. A special type of radiation is emitted in the reactor pool, which is called the Cherenkov radiation, and it gives water the soft blue glow. In the tank type of reactor, we can't see the reactor core like in a swimming pool type of reactor, because the fuel is enclosed in a tank which is filled with moderator and the tank is closed. Now coming to power reactors. Power reactors are classified into two categories: thermal reactors and fast reactors. Thermal reactors have moderators. We have discussed about moderators in our previous slides. These moderators, they slow down the neutrons. So thermal reactors basically operate with the slow neutrons. And the fast reactors, in the fast reactors, we do not have moderators. They operate only with fast neutrons. We will discuss in our later slides what are the importance of these fast reactors. Depending upon the type of moderator or coolant used in the reactor, thermal reactors are classified into light water reactor, which uses normal water as a coolant and moderator; heavy water reactor, which uses heavy water as a coolant and moderator; and gas cooled reactor, which uses gas as a coolant. Light water reactors are further categorized into pressurized water reactor and boiling water reactor. Pressurized water reactor constitutes the large majority of the world's nuclear power plants. A pressurized water reactor has two separate circulation systems, that is, the primary coolant circuit and the secondary coolant circuit. The primary coolant circuit circulates the coolant through the reactor core. Here in the reactor pressure vessel, the fuel rods transfer the energy released by fission and heating the water to around 300 degrees Celsius. We know that water boils and gets converted into steam at 100 degrees Celsius. So you may be wondering, at such a high temperature, why water does not boil. This is because the water is kept under pressure inside the primary coolant circuit at approximately 157 atmospheric pressure. This is done to increase its boiling point, because water in liquid form can take away the heat generated in the pressure vessel. If it is in vapor form, it will not take away the heat. In PWR, water in the primary coolant circuit is thus pressurized. Just to give you a feel, the pressure inside a pressure cooker is around 2 atmosphere. You may now get a feel of the high pressure in the primary coolant circuit. The heated water then flows from the reactor pressure vessel into the tubes of the steam generator, where it transfers its heat to low pressure water of a secondary coolant circuit, where steam is generated. The steam then drives the turbine, which spins the electrical generator. In a boiling water reactor, the coolant flows through the reactor core, where the heat in the fuel elements produced through nuclear fission heats the water to around 300 degrees Celsius, and the lower pressure of 70 atmospheres is maintained as compared to 157 atmospheres in the pressurized water reactor. So the water boils itself in the reactor pressure vessel and produces steam. This steam is directly used to drive the turbine, after which it is cooled in a condenser and is converted back to liquid water. This water is then returned to the reactor core after completing the loop. So this boiling water reactor has only one circuit, that is the primary coolant circuit, and it flows through the reactor core, it produces the steam, and the steam directly goes to the turbine. Pressurized heavy water reactor is very similar to the pressurized water reactors, that is PWR. The only difference is that it uses heavy water as a coolant instead of the normal water. Also, the fuel rods are not directly inserted into the reactor pressure vessel. Now, we have seen in a light water reactor, if this is a reactor pressure vessel, we have fuel rods inserted vertically. Okay, but in the case of reactor pressure vessel of PHWR, the fuel rods are placed horizontally in the reactor pressure vessel. You can see these are the pressure tubes inside which the fuel rods are placed, and the coolant flows through these pressure tubes. So the fuel elements, that is the fuel rods, are inserted inside these pressure tubes, which are placed horizontally in the reactor pressure vessel. They are not placed vertically. The coolant then flows through the steam generators, releasing the heat to the pool of pressure water. This pool of low pressure water turns into steam, which is then used to drive the electrical turbo generator. Now this is a picture of the fuel clusters which are placed inside the pressure tube of the pressurized heavy water reactor. And this is a fuel loading machine which is used to load the uranium fuel bundles inside the reactor core. So this is the actual picture. As of 2022, there are 220 research reactors operating worldwide and 441 power reactors in operation in some 30 countries around the world. So let us look at the breakup of this 441 power reactors operating worldwide. There are 268 pressurized water reactors operating in US, France, Japan, Russia and India. There are 94 boiling water reactors operating in US, Japan, Sweden and India. There are 40 pressurized heavy water reactors, PHWRs, operating in Canada, India, Argentina and South Korea. UK itself has 23 gas-cooled reactors in operations, and there are 12 light water graphite reactors, RBMK type of reactors, operating in Russia. There are 4 fast reactors operating in Japan, France, Russia, and India. India is the only developing nation to have indigenously established, demonstrated, and deployed nuclear reactors for electricity generation. So let's have a glimpse of our Indian nuclear program. India entered into nuclear age by establishing the Tata Institute of Fundamental Research, which is called as TIFR, on December 1945. It was an initiative taken by Dr. Homi Jahangir Bhabha, who is also called as the father of Indian nuclear program. Soon after independence, Atomic Energy Commission (AEC) of India was established on 10th of August 1948. AEC was placed directly under the control of Prime Minister of India, with Dr. Bhabha as the chairman of AEC. Under the AEC, the Department of Atomic Energy was created in 1954 to serve as the apex executive agency of the government in this field with the overall guidance of the AEC. It has its headquarters at Old Yacht Club building near the Gateway of India. You might have seen this building near the Gateway of India. Serious development of nuclear energy started in 1954 when construction began on Bhabha Atomic Research Center at Trondheim. Along with establishing a national base for nuclear materials, the DAE was also acquiring capabilities in the design, construction, and operation of nuclear reactors. And the first research reactor to be set up in 1956 was a light water moderated swimming pool type of reactor with a power of 1 megawatt thermal, and this reactor was called APSARA. It was the first reactor in Asia outside Russia. A second large research reactor called CIRUS was built jointly by India and Canada on July 10, 1960. You might have seen this dome-like structure while traveling from Gateway of India to the Elephanta Cave. Subsequently, the research reactor Zarlina achieved criticality on 14th of January 1961. This was the stepping stone towards the power reactors. And India's first boiling water nuclear power station at Tarapur was established in 1969. As the nuclear power program for the country was being formulated, it was planned to set up the required facilities for the nuclear power plants within India to have self-reliance in complete nuclear technology. And subsequently, Electronics Corporation of India (ECIL) was established in 1967 at Hyderabad, which provides strong indigenous support in electronic systems and instruments related to nuclear power plants. Uranium Corporation of India Limited (UCIL) was established in 1967 at Jadugura, Bihar. It is responsible for the processing of uranium from uranium mines. Nuclear Fuel Complex (NFC) was established in 1967 at Hyderabad to make the core components of nuclear reactors like fuel rods and control rods. Nuclear Power Corporation of India Limited (NPCIL) was established in 1987 with its headquarters at Mumbai, and it is responsible for design, construction, commissioning and operation of nuclear power reactors. Atomic Energy Regulatory Board (AERB) was established in 1983 at Mumbai. It is mainly responsible for the licensing and detailed scrutiny of the safety of nuclear power plants. Let's have a look on power reactors operating in India. As of now, we have 22 nuclear power reactors in operation. We have two boiling water reactors at Tarapur, which is in Maharashtra. Then we have PHWR, that is pressurized heavy water reactors. There are 6 units of PHWRs at Rajasthan, 2 units at Madras, 2 units of PHWRs at Narora Atomic Power Station, 2 units at Kakrapara, Gujarat, and 2 units of PHWRs again at Tarapur, and we have 4 units at Kaiga in Karnataka. We too have pressurized water reactor and they are operating at Kudamkulam. They are called VVR reactors and there are 2 units of PWR at Kudamkulam. So at present, we have a total installed capacity of 6780 megawatt electrical of nuclear energy. This is a picture of Narora nuclear power plant. You can see the cooling towers and the containment structures, which contains the pressure vessel and other nuclear components. Nuclear power plants are generally built near sea or lake so that they have a surplus supply of cooling water. Indian nuclear power plants have made landmark achievement in last 20 years. And two boiling water reactors at Tarapur, they have completed 52 years of operation. They are the oldest reactors in operation in the world. The capacity factor, which is defined as the measure of reactor's capacity to operate at its full strength, has improved significantly over last decade, indicating the consistent performance of Indian nuclear power plants. Recently, Kaiga nuclear power plant at Karnataka has set a world record for 962 days of safe and continuous operation. Let's have a look of the research reactors operating in India. BARC houses almost all the research reactors operating in India in the Trombay campus. The major application of research reactor is the production of radioisotopes. Radioisotopes are the atoms or the nucleus which emit radiation, and these radiations are useful in the field of agriculture, food technology, nuclear medicine, cancer diagnostics and treatment. Research reactors also act like a source of neutrons, and these neutrons are used for material testing and for scientific research. This is Dhruva reactor. It is one of the research reactors in BARC campus. It is a tank type research reactor. It produces 100 megawatt thermal of reactor power. It uses heavy water as a moderator and coolant and cadmium as a control rod. It has its applications in the production of radioisotopes in medical field and in electronics industry. This is a Kamini research reactor. It is placed in Madras. It is also a tank type research reactor. It produces 30 kilowatt thermal of reactor power. It is the only reactor in the world which is operating with uranium 233 fuel, which is produced from thorium. What is thorium? I will explain it later. It uses light water as a moderator and coolant and cadmium rod as control rods. Chandrayaan mission critical devices were successfully inspected at Kamini reactor. This is the upgraded form of APSARA reactor. I have spoken about APSARA reactor in my previous slides. It is a swimming pool type of reactor. You can see the reactor core and a bluish glow inside it, which is due to the selenophobe radiation. It produces 2 megawatt thermal of reactor power and light water as a coolant, and hafnium is used as a control rod. It achieved criticality recently in 2019. The reactor will be used for research in nuclear physics, material science, and radiation shielding. BARC is also designing advanced reactor for its futuristic application. One of them is Advanced Heavy Water Reactor. This is a schematic picture of EHWR, Advanced Heavy Water Reactor. The Advanced Heavy Water Reactor is the latest Indian design for the next generation nuclear reactor that burns thorium in its fuel pool. Thorium is a material which converts into nuclear fuel through nuclear reaction, and its energy potential is 3 times that of uranium. The utilization of thorium in power reactors presents an important long-term option for India. Then is the prototype fast breeder reactor. It is basically a fast reactor which operates with fast neutrons. Now, to maximize the benefit of nuclear energy and to provide a long-term energy supply, we are designing a fast breeder reactor which will not only produce electricity but will also give out fuel as an output. So it is a very innovative reactor and it is called breeder reactor. BARC is also developing reactor for hydrogen production with an aim to develop a high efficiency process of hydrogen production by splitting water. This is a schematic picture of such type of reactor. I'm sure now you can appreciate that how nuclear power generation has come a long way from the pioneering efforts of Enrico Fermi 8 decades ago. From the most basic experimental reactors, we have reached great heights in meeting our power requirements through technologically advanced reactors. These reactors are not only highly power generation intensive but also economical and safe. And we can see that our Indian nuclear power program has seen thousands and thousands of hours of safe and reliable nuclear operation. The high level of design, conservatism, and adherence to defense in depth criteria ensures that nuclear power is the way for our future. As we complete 75 years of independence, we as a nation continue to realize the need for self reliance and self empowerment. The Department of Atomic Energy has been in the forefront of efforts towards indigenous development of nuclear technology. On behalf of Department of Atomic Energy, I thank all of you for your keen interest and participation in this lecture. Jai Hind. INS lecture series contains other online lectures related to nuclear technology. Please refer to these lectures.